So all of you can hear me properly? Let me know once. Hello, hello. Perfect. So we were discussing about the topic, and we have finished the cantilever beam subjected to uniform distributed load, right? That thing we have completed, right? Uniformly distributed load for you for the cantilever beam. I think done, right? All of you, please check it out. Done. Note down the second case. A simply supported beam with a uniformly distributed load. Now for this case, we have to draw the shear force and bending moment diagram. Let's see how it goes. First of all, note on the diagram of this particularly loading figure. Okay, so this is a simply supported beam, and it is a symmetric loading condition they have given. So there is a support reaction will be coming RAV in the vertical direction, and here also it will be coming RBV. And what is the total load is there? The total load will be what? W into L, right? Total load will be W per unit length into total length. That will be total load, right? That will be total load. And that total load will be acting exactly at the midpoint of these UDL, right? Exactly at the midpoint of the UDL. And what will be the value of the reaction supports? So WL by 2, and this will be also be what? WL by 2. So that is how it goes. A simply supported beam with a uniformly distributed load. We have calculated the reaction forces. Now we have to calculate the shear force calculation first of all. Shear force calculation. Shear force calculation. So what is the shear force at point A? Suppose if I am moving from this side now, right? Yesterday I have moved from basically right to left, but today let me just move on to the what? Left to right. Similarly, sign convention we are going to follow for this also. When we are moving like this, it is positive, and whenever we have the downward, we will put negative. That's it. So shear force at A will be what? Plus WL by 2, right? What about shear force at the midpoint? C. What will be the shear force at midpoint? Shear force at midpoint will be what? Shear force at midpoint will be plus WL by 2. Now, my dear friend, at point C, shear force will be what? WL by 2. And because of this, what will be the value? What will be the value? It is exactly at a distance of L by 2. Then what will be the value? Exactly at point C, WL by 2 plus. But because of this loading condition might be acting at the midpoint of this section. Midpoint of this section WL by 2, and that is acting in the downward direction. Follow the sign convention and put what? 0. And what about the shear force at point B? What about the shear force at point B? What about the shear force at point B? Plus WL by 2 minus, because of whole loading condition, that is what? W into L minus WL. What will be the answer? Minus WL by 2. That will be the shear force at point B. But I said that whenever there is a concentrated load, you try to calculate 2 times. So now when you calculate 2 times, what will you will be getting? Minus WL by 2 plus WL by 2. Why plus? Follow this sign convention. If I'm moving like this, and whenever I found in the vertical direction, I will put positive sign, and the diagram is closed. Check it out, all of you. All of you, please check it out. Remember, at point C, there is a no concentrated load. It's a uniformly distributed load only. Some of you might be thinking, so that's the reason. Let me just, just wait, just wait, just wait. Some of you might be thinking, so let me draw a dotted line. There's a no concentrated load, but it's a uniformly distributed load. That's why only single time calculation. But at point B, 2-time calculation just because of what? Concentrated load, right? One will be there because of the what? Left hand side support, then left hand side loads, and the second value is what? Because of concentrated load that is acting exactly at the point B, right? Here also it's a dotted line. Do not confuse. There's a no concentrated load. Just imaginary thinking that a uniformly distributed load can be assumed to be behaving like a concentrated load, which is having a magnitude of total W into L, and exactly acting at the what? L by 2 distance. All of you are getting my point? All of you are understanding? With this particularly calculation, let's draw the shear force diagram. With this particularly calculation, let's draw the shear force diagram. At point C, at point A, and at point B. So here at point A, sorry. Now let me draw it with the line. So it will be exactly, my dear friend, straight line only. Sorry, it will be exactly the straight line. Do not confuse. So plus WL by 2 minus WL by 2. And this is what zero value we have. So it's a positive and it is a negative. So all of you are getting my point? Check it out. This will be your shear force diagram. Please note down, very important. So it's unlike what we have seen in the simply supported beam, subjected to the point load at the midsection. There it was something like this. But right now exactly zero, that's it. Right. Now how the bending moment diagram will look like? Let me give the option also, and let me give the time. Once it is done, let me know the shear force calculation as well as diagram. Done, all of you? Is it done? Perfect. Now try to focus on the bending moment calculation. I'm asking you the question, bending moment diagram will be, bending moment diagram. All of you please try yourself, will be option A, option A will be with the maximum value of the bending moment will be WL square by 8. That is what negative value. Option B with the positive value. Option C will be straight line, then parabola. Straight line, then parabola. Or option D will be like this. All of you, please try to participate in this particular, question, and let me know the answer. Take your time. I told you that whenever we have the uniformly distributed load, try to, if you are not able to get it directly by points, shortcut, try to use section method. If some of you are very much able to visualize the condition, then you can easily disregard, you can easily reject the options first in a very first instant. Do not think of two options. Two options can be easily eliminated. Tell me guys, all of you. Yes. A. Only one person is giving A, B. Okay. So remember, B option is correct. B option is correct. Now, why the B option will be correct? There is a reason for that, right? Now, try to think. Section method, the bending moment calculation. The bending moment calculation. What will be the bending moment calculation would be there, right? That is what we have to see. So let me just take it out from the, suppose left hand side. Suppose let me take it out from the left hand side. I'm taking one cross section at a distance of x. The value is what? WL by 2, that RB value. Here also, because of simply supported, both will be same. Because of simply supported, both will be same, my dear friend. Both will be same. Both will be same. Now, try to understand what is the bending moment at a particular cross section XX. Can I say WL by 2 into X? Can I say WL by 2 into X if you follow the sign convention, my dear friend? Like this, positive. And when you follow the sign convention like this, it is negative. Check it out, all of you. So WL by 2 into X. Perfect. Minus of this particular loading condition. This loading condition will be trying to providing this total load of magnitude W into X. And that is going to be acting at a distance of X by 2. And that is what? Negative. So W into X, that is a force value, into distance. That is what? X by 2. So WL by 2 into X minus W into X square by 2. That is what your bending moment at XX. Now, some of you just follow the equation. They might be thinking, sir, linear parabola kind of thing. The thoughts will come. That's why I kept the option C and D also. Now, bending moment at x equal to 0. At x equal to 0, that means at point B only. Exactly at point B, if I'm just calculating, its value is 0. Even in the conclusion point also, I have given that at the simply supported ends, the bending moment will be 0. What is the bending moment at exactly at the midpoint at point C? What is the bending moment at point C? Exactly at a distance x equal to L by 2. So W into L by 2 into L by 2, W by 2, L square by 4. So W into L square by 4 minus W into L square by 8. So that is going to be answer as W into L square by 8. That is what the bending moment at C. That is what you have the bending moment at C. All of you, please check it out. Please check it out. Please check it out. Perfect. Sorry. What is the bending moment? Now try to calculate the bending moment exactly at point A. Even it is a hinge support, that will be 0, but not believing, you can check it out. At x equal to L. At x equal to L, try to calculate W into L by 2 into L minus W into L square by 2. So both will cancel out, it's a 0 value. So now it's a symmetric parabola with the maximum value at the midpoint. You will be getting what? Exactly like this. Note down, very important. So all of you are understanding my point? Yes or no, guys? All of you are able to follow me? This is sometimes this is called hogging bending moment. And this is called sagging bending moment. Please note down sagging and hogging bending moment. Very, very important. So all of you are understanding? Is it done, all of you? All of you have noted down? Yes, all of you have noted down? Perfect. All of you done? Can I move to the next question? Perfect. Thank you. Now, so we'll try to see the another question. Yeah, little bit different, but sometime whenever the support can be externally, support can be internally also, like this. This is called when the load is just outside of this particular domain, that is reaction. This is called overhanging beam. Right? So this is one kind of question from the overhanging beam. Very, very important. Calculate the shear force and bending moment at the midpoint of at the midpoint. That means you can consider point D. So 2 plus 4, 4 plus 4, 8, exactly at a distance 4 meter from the A, we need to calculate the shear force and bending moment. For that, we have to calculate the reaction force. What will be the reaction forces? RB plus RC, that must be C. Summation of forces in the y direction must be 0. That we need to do first of all. And accordingly, what we will calculate? 80 kilonewton. Let's see how it goes. Now you just take summation of moment about B must be 0. Summation of moment about B must be 0. Now when you take the summation of B, summation of moment about B must be 0. So RC into this RC. This is what we have RB. So RC into 2. That is equal to this uniformly distributed load. That is 10 into 8, that is 80. And exactly it is going to be acting at a distance of what? Middle section. And middle section distance is what? Exactly is what? Sorry, RC into 4. RC into 4, the distance is what? About B and C? 4. But this distance will be 2. So what will be the answer? 40 kilonewton. And similarly, what will be the answer for this RB? Will also be same. Note down, very important. Of course, both because of symmetricity nature of the loading condition, you can say that RB and RC will be equal. Now you can just calculate the shear force and bending moment just by the method of, what I said, that is shortcut method. So what is the shear force at D? Directly calculate. Because of this loading condition, see, I can draw over here. First of all, because of this loading condition and because of this reaction, you just calculate from the left hand side. I said that shear force is summation of forces either on the left side or on the right side. Do not consider both the sides at a time, right? Forget the loading condition in the right side. So whenever the left side forces will be there, you know the sign convention. What will be the sign convention? Plus RB. RB is what? 80. Minus of this loading condition, that is what we have 10 kilonewton into 4, because distance is what? 2, 2. 10 into 4. 10 into 4. That will be the shear force. And what will be the answer? RB is 8. RB is what? 40, right? RB is 40. 40 minus 40, what will be the answer? 0 kilonewton, right? So the very first option that you are getting, what? Directly A option. Do not calculate bending moment. Do not calculate the bending moment. Or sometime, see, this question they have framed in such a way that they have not mentioned respectively. So it can be anything. The first, whatever they mentioned, that can be shear force, that can be bending moment. We don't know. So it's better you calculate bending moment also. So bending moment at point D will be, because of this loading condition, RB positive, because it's a sagging bending moment. Sagging bending moment because of RB into distance 2. So RB is what? 40 into 2, that is 80 kilonewton meter. Minus of this loading condition is what? Hogging bending moment, that is 10 into 4, that is 40. And it is going to be acting at a distance of what? 2 meter from this point D, that is 82. So 80 minus 80, you know that it's a 0 kilonewton meter. So answer is what? A. Understanding my point? All of you? All of you are understanding what I'm saying? Please check it out. Done. If it is done, we can just move to the next question. Let me know in the chat section. Perfect. So note down at the point of contraflexure. Sir, what is the meaning of contraflexure? Right. So what is the meaning of, anybody know what is a contraflexure? Maximum time you will face this question in the what? In PSU, not in the gate examination. So hardly they ask, maybe not in a single time also. No single time also in the gate mechanical. In civil, frequently this question appears. So contraflexure means the point about which the bending moment changes its sign. The point about which bending moment changes its sign called as contraflexion. Contraflexion. Very important. So this option will be correct, right? Now, in which condition we can show that the bending moment is changing its sign? Under which loading condition we can see this thing? Can you imagine the situation? Work out the example like where we can imagine the situation. Tell me, guys. Any situation you are able to remember that where you can find the bending moment to be, exact, just become zero. Changes its sign means just become zero, you can say. Where we can find, yeah. So let me just give the example of, yeah, you're just moving ahead of this. If you just tell me in the context of what we have seen the beam condition. So at the middle section, if I just apply the moment, if I just apply the bending moment, simply supported beam, but concentrated movement is there. Instead of concentrated load, the concentrated movement is there and movement is acting. You know that the reaction forces will be directly I'm calculating. You can just calculate by the static equilibrium conditions, but see the movement I'm just doing by shortcut. If the movement is acting like this, the reaction movement should be created like this, by this, by this, minus m by L, m by L. Understanding my point? All of you are understanding what I'm saying? RA will be RA, this is the point A, this is the point C, this is the point B. It will be acting in the upward direction. Of course, I'm putting more plus sign only because as the arrow I kept what? In the downward directions, right? Now, how I got it? You can apply static equilibrium conditions or you can just do the shortcut. When external movement is acting like this, reaction movement must be opposite of that. Who will able to create the reaction movement? RB and RA only, right? In such a way that they will offer the resistance like this. Now, okay, that is a part and parcel of the conditions. Now, that is a shortcut method for finding the reaction forces. Now, my purpose of to basically show this question is that try to draw the bending moment diagram for this. Try to draw the bending moment diagram for this. What will be the bending moment diagram? What will be the bending moment at point A? What will be the bending moment at point A? 0. What is the bending moment at point C? What is the bending moment at point C? Minus m by L into L by 2, right? So it's a minus m by 2. 2 time or 1 time calculation? Tell me, guys. 2 time or 1 time calculation? 2 time or 1 time calculation? Tell me, guys. Quickly. Follow the conclusion. Follow the conclusions. Why 1 time? When there is external movement is there, concentrated movement is there, concentrated load is there. Whenever concentrated load is there, calculate shear force 2 times. Whenever there is a concentrated movement, calculate the bending moment 2 times. I said already. Check it out. So here bending moment at point C will be minus m by 2 plus m. That is what m by 2. Now some of you will confuse or y plus. Y plus. I said that we are moving like this. Whenever we are moving like this, the first will say just left to the C. And the second one will say just to the right. Just to the right means it will able to create the movement like this. And if you just follow the sign convention at any cross section, it is plus only, right? The bending moment at point B will be, I am not calculating. I believe that you will be getting 0, but not believing. For that purpose, let me just do once again m by L into L minus m or plus m. It is minus, it is plus 0, big 0. Check it out. All of you, please check it out. So all of you, whatever the hard work we did, for that only we are getting the results, right? This will be your diagram. If anybody not understood, let me know, guys. If anybody not understanding, let me know. So this is the point, my dear friend, where this particular point, point C, it's called as point of contraflexion. No doubt. It is the point of contraflexure where the bending moment just becomes zero or changes its sign from minus to plus. Understanding or not? Please check it out, verify it, and then let me know. I know that some of you having confusion in the principal stress and strain. How many of you have confusion? Please let me know. How many of you have the confusion in principal stress and strain? That is 3D stress, 2D stress, plane stress, plane strain, 3D stress, 3D strain, bow circle. In this one, any doubt is there? Tell me, guys. Yes. Yeah, I know that the doubt definitely will be there because apart from BC Pneumonia, no other book is able to justify that explanation actually. They are exactly correct, but you need to be, understand each and everything in detailing. Now, so some of you who's very much curious why we are calculating 2 times, you can just note down bending moment just left of C. And this you can write bending moment right of C. Right side of the C. Right of C. Left of C, right of C. Note down, very important. Point of contraflexure. Once it is done, please let me know. Done, all of you? Is it done? Yes. Please let me know. Perfect. So this is what the question we have, little bit tricky question. Whatever the supports we have seen, yes, as of now, whatever the support we have seen, that is the external support. Whatever the support we have seen, that is external support. My dear friend, you are welcome to the question where they mentioned that the cantilever OP, the cantilever OP, the cantilever OP is joined with the another PQ by the pin joint. By the pin joint. And let me just show the pin joint by the different color. Pin joint. Pin joint. This pin joint, my dear friend, this is called internal hinge. This is called internal hinge. So varieties of the problem I am covering so that you will not be having any difficulty, my dear friend. After some subject, once it is finished, your favorite subject will be, my dear friend, this particular strength of material only. Because here things are very easy. And if concepts are clear and the fundamental things are clear, you will play with the questions actually here. So now that is what our question number 4, I think. Now they are asking that when the load is 10 kilonewton is applied at the midpoint of the beam, there is a 2 beam, one beam, another beam. They join together by the what? Some kind of internal hinge. Not exactly what I shown, but something like this. 2 beam, OP and PQ. They will be connected with each other at the point P with some kind of internal hinge. With some kind of internal hinge, my dear friend, right? The load has been applied at the midpoint of the PQ beam. They are asking what is the maximum, what is the magnitude of the bending moment at the fixed end. So before let me explain this problem, I just want to know the answer from Any one of you, at least some guessing, maybe, or if you are able to solve, you are welcome to solve and let me know the answer. We'll discuss about this internal hinge, a very important, very hot topic. Recently only they asked this question in, I think, HC paper, engineering science paper in GATE. So definitely it is going to be worth solving this particular question. Try to understand. Try to understand. There is a strategy, right? So how to solve this? Treat the two beams separately. Treat the two beams for this question. Treat beams separately. You know, or you can take the beams separately and try to solve by static equilibrium conditions. Take the beams separately. Separately, we are going to take the beams. That means first I'm going to take the cantilever beam OP. I'm going to take the cantilever beam OP and OP, and second beam I'm going to take this simply supported beam, something like this I will assume, and my reaction will be RP, and here my reaction will be RQ, and there is a midpoint load that is going to be acting 10 kilonewton. If here it is RP, if here it is RP, my dear friend, here it will be acting in this direction. If you just combine over here, if you just combine, this will become what? One particular beam, which is being connected with each other by joint P, internal joint P, internal hinge we say. Rather to say joint, we say internal hinge. Now, this particular thing you can solve. It's a simply supported beam. It's a simply supported beam with the symmetry. So whenever the symmetry is there, you know that RP will be what? 5 kilonewton and RD will be what? 5 kilonewton. Similarly, this RB will transfer here also 5 kilonewton, and you know that for this case they are asking what is the bending moment at point O. So bending moment at point O will be RP into 2. That is what 5 into 2. That is what we have 10 kilonewton meter. All of you are understanding strategy how to solve whenever the question will be coming about the internal hinge. Please note it down. Very, very important, guys. Now, some of you might be thinking, sir, why we are treating separately? Why we can't solve having the combined beam together? Suppose some of you might be thinking like that, then you might be having statically indeterminate conditions. How? 3 unknowns: RQ, RO, external moment. 3 unknowns, but we have only two equations. What are the 2 equations we have? Summation of m about any point must be 0, and summation of forces in the y direction must be 0. 2 conditions, 3 unknowns. Static indeterminacy will be there. To solve that extra equation, we are treating the 2 beams separately. Understanding or not, all of you? Please check it out. All of you, please check it out. All of you understanding? Perfect. Perfect. Just note down quickly. So here, two 2.5, just wait. Okay, done all of you? Can I move to the next one? Can I move to the next one? Yes. Perfect. Now try to solve this one. Try to solve this one. Take your time. 2 minutes of time I'm giving to you. Have patience and try to solve this one. Yes. Take your time. We're not in a hurry. Little bit lengthy question, I would say. Sorry, I was saying before question, right? Sorry, guys. This was the question, right? All of you? So this is just like a, uniformly varying load we call. Whenever the loading has been given something like this, then we call this to be uniformly varying load. Whatever we have seen before question, that is uniformly distributed load. This is called uniformly varying load, UVL. So very first of all, we need to calculate the reactions. I'm not going to calculate the reaction, guys. You can just follow any summation of Fy must be 0 and summation of moment about A must be 0. With the help of these two, I'm just giving you the values of Ra and Rb. That is 4.8 kilonewton. And Rb would be, my value will be 7.8 kilonewton. Check it out. Please check it out. So somewhat difficult to solve within 2 minutes, right? It requires a lot of practice, a lot of conceptual clarity, and more apart from it, you need practice in the diagrams and all. So they're asking what is the location of the zero shear stress from the point A. So I'm taking any location at X distance from the point A like this, and I'm going to calculate the shear force at that location, and I'm going to equate towards 0, my dear friend. Simply that is my simple strategy, I would say. So RA will be what? 4.8 into 1. We are not calculating movement, we are calculating the shear force. Minus of what? This loading condition. I'm drawing once again here. This loading condition at a location XX. Now, my dear friend, tell me, if this particular value, maximum value is 7.2, then what about this value at this location? What will be the value? Can we follow similar triangle, my dear friend? Suppose at this location load is what? WXX, and this distance is X, and what about this distance, my dear friend? 3 meter. Try to follow similar triangle. 7.2 divided by what? 3. WXX divided by what? X. So what is the WXX? 2.4x, right? Check it out. All of you, please check it out. Are you getting comfortably? 2.4 into x, right? Perfect. Now, my different. So 2.4 into x, that is this value. What about the total area? Total load will be half of this height and this particular length. So W into x. Now this load is acting at this particular distance from what? From this location, it is going to be acting at a distance of x by 3. Here comes the center of gravity, my dear friend. Very, very important. So 2.4 into x. 2.4 into x. Sorry, this value will be 2.4 into x. This value will be 2.4 into x into x. So what I can write? Into x by 3. That I am going to equate to what? 0. That what I'm going to equate to what? 0, my dear friend. Please check it out, all of you. All of you, please check it out. Understanding or not? So 4.8, that will be equal to 4.8, that is going to be equal to check it out, all of you. No mistake must be there. Yes. So that is perfect. Sorry, we are calculating not bending moment. We are not calculating any bending moment. We are calculating the shear force. So do not multiply with the distance. Understanding what I'm saying? This will be only the load. This is also load. This is also load, right? So 2.4 divided by 2 into x square. So x will be what? 2 meter. Exactly at a distance of 2 meter. Maybe here, the shear force, if you draw the diagram, shear force will be 0. Understanding? All of you are understanding what I'm saying? Tell me, guys. Perfect. Note down, please. Very important. Do not multiply with x by 3. When you are calculating the bending moment, then you can multiply with the, something you say x by 3. Otherwise, do not multiply. Now, once it is done, please let me know. The last problem for this shear force and bending moment diagram we can see, and then we can start bending stress. Please note down. Then can I move to the next one? In this particular question, finding the reaction forces might be tough. That's it. Anybody who is facing the problem in calculation of the reaction forces, raise your hands. Tell me, guys, in the chat section. Anybody is there who is just facing the problem in finding the reaction forces? Yes. Tell me, guys. All of you, please tell me. Can I move to the next one, or having any doubt in the reaction forces finding? Perfect. Note on the last problem, and then we'll wrap up this and we'll do what? Bending stress. Take your time, 2 minutes of time, maximum to maximum, and try to solve it. So, what is the answer? What is the answer, guys? Okay, so C, let me check. I think incorrect. Incorrect. Find the maximum bending moment and the position from the support A they are asking. Again, it's little bit, tough question, I would say. Not that much easy as you might be predicting, but with the logic, you can just go with that and you can just follow. Try to follow me. So first of all, you need to find the reaction forces. Of course, here one correction you can just make it out. There cannot be two roller support. There must be one in support. So one would be, reaction forces will be coming in this direction, and reaction forces will be coming in this direction. And by making the summation of force y to be 0 and summation of moment about A must be 0, with the help of this one, you can calculate RAV to be, let me directly write, 98 kilonewton. Check it out, any one of you. And RB will be 82 kilonewton. Please check it out. Are you getting these answers? Reaction forces? Sometimes it is very difficult to get it the point where the maximum bending moment is there, right? Even though you calculate by my shortcut method, you will try to find the answer for point A, point C, point D, point E, point B, but sometime, somewhere here or maybe here, the bending moment will be maximum. How can you identify? You know that the relationship force is equal to dm by dx. When force will be 0, dm by dx will be 0. From the mathematics, it's saying that In the bending moment diagram, whenever the slope of the bending moment is 0, there the bending moment is either maximum or minima. Understanding or not? That idea we are getting, where the shear force will be 0, there the bending moment will be maximum. So what we will do? We will take a cross section, my dear friend, and we will try to calculate. We will try to calculate at what location shear force is 0, rather than finding the bending moment at each and every location. Understanding my point or not? Check it out. Whatever I said, please check it out. Correct or incorrect? Please check it out, all of you guys. All of you are understanding my point or not? Let's see whether the bending moment is maximum exactly at point C or not, or less than 5 meter distance. That we need to calculate, right? So we will calculate the shear force at a distance xx from A. Suppose we are calculating at this particular distance. So what is the shear force, guys? RAB, positive or negative? Sir, positive. Sir, positive. What about 20? Negative, sir. What about this loading condition? What about this loading conditions? What about this loading condition, guys? I think they already mentioned 20 kilonewton per meter, right? So please make a correction that it's a loading rate, load rating only for this one. There is no external load. All of you are understanding my point? The figure is something like this. There is no vertical concentrated load, right? So 20 into x, that must be equal to 0. So what is the x value? 4.9 meter, right? So exactly at this distance, my dear friend, shear force is 0. Bending moment will be maximum at that location, believe me. You can take it as a homework. After calculating the maximum bending moment, you can just calculate at A point, at C point, at D point, at E point, at B point. Of course, point A 0, point B 0. You can check it out and you can verify it that where you are getting the maximum bending moment at point C, D, E, and one more point is point F. Check all the 4 points. Answer will be coming maximum at 4.9 meter distance only. And what is the answer? RAB into distance will be what? 4.9 meter minus W into X by 2. That is 20 into 4.9. That is the load. And load is going to be acting at a distance half. So RAB is what? 98 into 4.9 minus 10 into 4.9 whole square. So now when you calculate, the answer must be coming 240.1 Newton meter. B option will be coming. And what distance? 4.9 meter from A point. Right? Understanding or not? Tell me, guys. Tell me, guys. If suppose they would have asked, what will be the maximum bending moment position from the point B? The answer must be 5.1 meter from B. Maximum bending moment location. All of you are understanding or not what I'm saying actually? Please let me know. Do not confuse. Please let me know. Whatever the confusion is there, try to tell me. All of you are getting my point or not? Yes. Perfect. Can I move to the next one? Shall we move to the next chapter? That is a very, very important chapter. That is bending stress. Yes. Done. Done, right? Okay, fine. Right. So not only bending stresses, in simple bending, chapter 3 will be up to thermal stress and elastic constant and statically determinate and indeterminate beam structure. Total I'm combining with the chapter number 1. Chapter 2 is what? Shear force and bending moment diagram. This will be my chapter 3. Bending stresses in the simple beams. right? So we will talk about the pure bending, pure bending. Pure bending. Now tell me whether pure bending is possible or not. Whether pure bending is possible or not. Question mark. Whether pure bending would be possible or not possible. Just think and tell. Pure bending means no shear force. No shear force. Shear force would be zero. Simply. Shear force must be zero for having the pure bending case. Remember. Tell me guys, quickly. So whenever there is a cantilever beam, let me give you example. The answer is yes, and sometimes the answer is no also. Check it out. A cantilever beam which is having a point A and point B subjected to external movement. So whenever I used to take the pause in between the lecture, I actually just try to give the time so that you can think of any example. So that whenever I used to dictate the example, you would just catch my point. Okay, got it. Something like that. If at that same moment, if I just tell you, it is just like a spoon feeding kind of thing. Understanding or not, all of you? Tell me, guys. Yes, because believe me, suppose if I invest 80 hours of the time in some lecture, suppose solving each and every problem from Timo and Gere, taking each and every problem from the Hibbeler, taking each and every problem from the BC Pneumonia also. Suppose I just prepare you for the worst and worst condition, but there's no guarantee. Suppose I solve 500 questions in the classroom, gate problems, but there's no guarantee that when first question will come in actual gate paper, I'm not taking guarantee that all of you will able to solve that question. There is no guarantee. Question will be there within syllabus only, and whatever the topic we have covered, but there's no guarantee you will be able to apply the aptitude. There's no guarantee. Nobody can take the guarantee. Even if you are learning from IT professor also, he will also tell you that I'm not taking any guarantee, my dear friend. That all depends how have you applied the logic in solving those 500 questions, whether you applied any brains or not. Right? That's why the live classes attending is much important rather than seeing the recording actually. Right? I know that same interface will be there, same logic will be there. What I'm saying actually, if I'm taking the pause will be coming in the recording also. But in the live class, you can think and you can ask the question also. Right? So at the initial day of the class, many of you have the enthusiasm and they attended like anything. 15 students, but now suddenly got reduced. Right? So that's the reason I'm saying that. You should have the motivation from the starting day to the end date. It should not like only first day you are learning like anything and the next day sleeping. It shouldn't happen. You're just fooling yourself. Nothing much will be. No, see, loss is not there. Money loss is not there. You're not paying anything. It's a completely free course. So money part, you are completely, done. No, actually loss will be there. But my dear friend, more than money loss, time loss will be there. Suppose you are fooling yourself that you are preparing for the HL examination, and if you are not able to make it, then you are totally wasting your time actually, right? You can do something else. I'm saying that. So please try to understand the seriousness of this particular time, right? Whatever the seriousness is must be there, that has to be there. Believe me, this is 2022. This is not your 2016 or 17, where actually the competition was little bit. There also competition was there, but that much was, explosive, exploring things were not there. Actually, net is not there. Internet connections, right? If you just go to the Bangalore city and Hyderabad metro city, there the fiber connection and Wi-Fi connections are there, broadband connection. But now the villages also, they just enter with the what, Geo and all kind of thing. So they have access for all the NPTEL lecture also. They can also watch. They can also solve the good number of problems also. So automatically competition has been raised drastically like anything, giantly, right? So believe me, understand these things. Now, see, so here it's a simply free class. Doesn't mean that whatever the YouTube class is going on, it's same kind of thing is running over here. No, it's a totally completely professional. Whatever the things are provided over here, and up to the mark. You can just verify by solving the previous year question also, right? Yeah. So come to the point, pure bending, whether it's possible or not. So pure bending, first of all, is the kind of thing where in any beam, at any particular cross section, when there is a no shear force, right, only bending moment is there, and bending moment must be constant. That is also one more condition. It should not vary. The bending moment must be constant, my dear friend. Then together these two conditions will be called as pure bending. Together these two conditions will be called as, my dear friend, pure bending. Please note down up to this point. Now the cantilever beam which is there, a cantilever beam which is there, which is having a distance L. Now if I draw the bending moment diagram, so you know that at point B, bending moment will be what? If I am moving from this, I need to just move little bit of left side and I will find that it's a negative one. And the similar situation might be there at the point A also, that is minus M. But there is external moment that is acting at this point, and that is going to create the positive. Two-time calculation will be there at the point A. Why two-time? External moment, external reaction moment is also acting. So minus M plus M, closing the diagram, that is 0. So simply my structure will be like this. Bending moment diagram will be like this. M. This will be my bending moment diagram. And now if I'll ask you shear force, nothing is there. RAV 0. No vertical loading. Shear force diagram will look like this. Single line. Having a 0 magnitude, that is the answer for shear force diagram. Along the any cross section, if we take it out, the shear force is 0. That is called pure bending. Along with that, the bending moment is what? Constant, my dear friend. Bending moment is not varying like linear one, like this or like this, right? Suppose anywhere in the beam, yeah, that is a very good thing. Bending moment diagram is something like this. So from this section to this section, the bending moment is what? Constant. The bending moment is constant. And if the shear force will be 0 at this section, then we will say that particular cross section of the beam, that is that portion of the beam is what? Under pure bending, right? So sometimes complete length of the beam may not be under pure bending, but some part of the beam may be under pure bending. Of course, this is an exceptional case. Whatever the example number one, I'm saying that it is completely exceptional. But sometimes it is possible to have the pure bending across the length also. So this is what example number 2, right? Please note down. This I cannot call, varying bending moment to be, this I cannot call pure bending, because shear force is equal to what? Dm by dx. The moment I am going to have the slope, the shear force will not be 0. The moment if I draw the slope of this diagram, for this particular part, slope for this part BC, slope is 0. Slope is 0 actually. Shear force will be 0. No 0 shear force, bending moment constant. That is what the condition for pure bending. Understanding or not, all of? All of your understanding why we require the concept of not varying bending moment, constant bending moment, right? To understand this pure bending, you need to watch NPTEL for at least 6 to 8 hours that you need to invest for this slide only. Whatever the slide we have just completed, for that IIT, if you follow IIT Madras lecture, that is going to take 8 hours. Why to invest time there, right? We can just save the time and we can invest the particular thing in the solving the questions. of that IIT professors, or you can just take it out, from NPTEL directly. You can take the PDF, right? And of course, many question sources are there. There's no limitation at all from that particular point. But the limitation will be there while applying the concept, while applying the aptitude, my dear friend. Remember these things, very important. So pure bending, no shear force, and bending moment must be constant. Now, once it is done, let me know. Right, so shear force will be equal to dm by dx. Of course, shear force will be 0. dm must be 0. dm must be 0 means bending moment is constant. That is what dm by dx is 0, right? From the mathematics also, it is proving that thing. Now, once it is done, then please let me know. Done, right? I think. Perfect. Now, not only assumptions, what we have seen, there is a fourth assumptions, but I just did not mention over here. Just note on the 3 assumptions. I will mention the 4th assumptions. The material must be perfectly homogeneous, right? And isotropic. Of course, that is the rules for every, what you can say, that strength of material. The beam material is stressed within the elastic limit, and it should follow Hooke's law. It should be within the elastic limit, and it should follow Hooke's law. I said that while drawing the mild steel diagram. I mentioned that it should be, our strength of material is what? This zone. The moment you cross this zone, production will come. Some of you might be thinking, sir, what is the difference between homogeneous and, this thing, isotropic material? Anybody know? Take your time, 2 minutes of time, think and tell me. In fact, in the bracket also, they mention each and everything. And tell me the example of those materials. Tell me the examples of, those materials. Just think and tell. Very simple. But I would say that in PSU, these questions and this question they have asked not less than, not less than 50 times. More than 50 times only they have asked. If you just come across different PSU examination in past 5 years, more than 50 times they ask. They are giving the any definition, random definition. They are asking whether it's a homogeneous or isotropic, non-homogeneous, anisotropic, all this kind of structures, right? So first of all, we are going to learn what are all those things, right? So relevancy of the topic must be there. Remember this thing. Keep it in mind. So just try to think and tell me homogeneous material. We will try to learn homogeneous material. Homogeneous material. Homogeneous material is saying that in any body or any particle, if any body, non-rigid body or deformable body, when the elastic properties are same at all the points in a given direction, then I would say that material to be homogeneous material. That means if I assume my x direction, if I assume my y direction, if I assume my z direction, this is a point P1. Elastic properties are same at all the points at a given directions. At a given direction, my properties, let's suppose that at x direction, my elastic property is what? Young's modulus, suppose Ex. In y direction, it's Ey. Is z direction, it's suppose z, Ez. Then what I can say? At point P2 also, at the location x, in the direction x, my this particular Ex will be same, my Ey will be same, and Ez will be same. Understanding or not? Please check it out. Suppose any material is there. This is the material number 1. Whatever I said, this is a point in that material. 2 point I have considered. This is what a material number 1 we have. Now, if I consider 2 point P1 and P2 in the another material, non-homogeneous material, suppose in this direction E is what? Ex. In this direction E will be what? Ex dash. Whether we can call this to be homogeneous? At all the point in a given direction. in a given direction, X direction, Y direction, Z direction. That is the meaning of directions. At a particular direction, at all the points in that direction, whether properties are same or not. No, it's a different one. So this is called non-homogeneous material. Understanding the meaning? And this material should be said there to be called as homogeneous material. Tell me guys, all of you are understanding my point or not? Perfect. Exactly, you can draw vertical line. Exactly, you can draw whatever the vertical line you have drawn for the point B. There's a no difference. The direction must be same at all the point in that direction. At all the points in that direction, property must be same. Elastic property must be same. That is the meaning of homogeneous material. Right now, the next thing would be my different isotropic material. What is the meaning of isotropic material? First of all, not on the homogeneous definition, right? So homogeneous definition where we can write. Okay, I can remove this one. Okay, so homogeneous material will be elastic properties are same at all the points in a given direction. No. At all the points in a given direction by different, right? So it's a directional dependent property, we can say. What about the isotropic? Elastic properties are same in all the direction at a particular given point. That means if any material would be there, point P1 is there, then elastic property will be same in all the direction, will be even only. Suppose even. And at point P2, the elastic property might be different. E2. So it's not necessarily to have the same property in a particular direction at all the points, but at all the at a given point. Suppose P1 point is given in all the direction, it has to have the same. Properties. It should not like this Ex and Ey. For this one, Ex and Ey must be same at different particular points. Understanding? It can have different E1 and E2 for the different points, but at all the direction the property must be same. Many confusion would be there in the examination by different. They will give this definition and they will put the option homogeneous, isotropic, non-isotropic, anisotropic, and D option will be something else, right? Something kind of orthotropic material like those. Understanding or not, all of you? So note on the definition, that is the definition is very important. Yeah, so first of all, note on the diagram. This diagram is very important. This material we can call isotropic material. Do not follow Google answer. Remember, whenever you are searching any answer, if you are just searching the definition or concept or formula in the Google, there may not be guaranteed that it will be always 100% true. And suppose any answers you are learning in the Quora, try to verify whether upwards are very, very high or not. In the downward, upwards will be there, thumbs up kind of thing. If that is going to be very, very high, and if you after learning this particular Quora answer, you find that all the points they mention is genuine answer is there, right? Many upwards are there, and there is no fake answers are there. That particular Quora answer you can follow. Otherwise, simply reject it. Simply reject Wikipedia answer, because Wikipedia answer is just made by like you and me only, students only, right? So there is no official guarantee until unless you follow the NPTEL PDF, NPTEL kind of things. You cannot believe in the whatever the market in the Google market, whatever the answers has been thrown. Simply they are kind of junk, we can say. In YouTube also, whenever you follow any lecture, try to see whether it is genuine or not, whether this concept has been, whatever the concept has been delivered by that particular person is exact, correct or not, right? At least verify from the other sources also, so that you can continue that lecture. Now, suppose you are learning at the, because some of you are in the final year, so you might be facing very much difficulty in this thing only, right? While finding the suitable sources for the studying, right? A lot of confusion will be there, definitely. So try to clear at least for this particular point that what's I need to study, what are all the sources, you must be clear in that. And after that, enjoy like anything, whatever the, hard work you can put from your side. That is solving the question like anything. And writing the test series. At least 2 to 3 institute, you can take it out the test series. And suppose you are finishing any subject, straight away try to write down the test series of that particular subject wise, and verify whether you are going in the right direction or not, right? Suppose you are planning for the gate, I'm saying that. If not, there's no problem. Now done. Can we have the definition? Once it is finished, let me know. Done, all of you? Perfect. So we can just note on quickly the definition of isotropic material. Note down. Same elastic property. Same elastic properties in all the direction at a given point, right? Is called isotropic material. Right? So if a material is homogeneous and isotropic, both, then the direction at all the point, at all the given directions will be same, right? Yes or no, guys? Yes or no, guys? All these examples of the material, engineering material, pipe, steel, cast iron, all the materials are both homogeneous and isotropic, remember. Then, sir, what is the example of the orthotropic material? Note down. Orthotropic material. I'm not giving any detailed idea about this thing because that thing will be covered in the what course of the gate examination. Right now, do not follow, means don't focus much on this orthotropic material. Just note on the examples. Wood, graphite. Why we are calling wood to be orthotropic? That are all the matter of detailed discussion actually. Right? Any layered material. Layered material means just like a plywood kind of thing. And there's a one more category, anisotropic material. Anisotropic material. So here example will be, see, anisotropic means just opposite of the isotropic. At all the given directions, sorry, in all the direction property will be different at a particular point. At a particular point, in all the direction property will be different. E1 in X direction, E2 in Y direction, E3 in Z direction, kind of things. An example will be glass. Whatever the glasses of your house, that is the anisotropic material, my different, right? So stone with the cracks. Any stone if we take and there is a crack, that will make the material anisotropic. In engineering, but material science you will understand in detail. So yeah. The third assumptions, whatever we are seeing, that I will discuss, and the fourth, which I mentioned, that we will discuss while understanding the diagram of the bending, how the bending actually happening. Now, second is clear by the graph of mild steel stress versus strain diagram. Now, once it is done, let me know. Yeah, done. Bending stress. Yeah, bending stress we will try to learn. We also call sigma B. So remember, if somebody will ask you normal stress, whenever the load is acting perpendicular to the cross section. So remember, if somebody will ask you normal stress, how many types? You must say two types. Axial stress, bending stress. Both are called as normal stress. Understanding? Axial stress, normal stress. Bending stress, that is also normal stress, right? Note down this thing also, a lot of confusion might be there. Please note down. Now coming to the point, let's suppose that I'm taking any material. A cantilever beam which is having a cross section something like this, B and D. The cross section is what? Rectangular. Suppose I'm taking the cross section to be rectangular, my dear friend. Suppose, and having a length to be, L. Suppose now I'm applying the hogging bending moment like this. I'm at the extreme end. How we can represent it by normal load condition wise? Can we represent it something like this? Check it out. I'm drawing very carefully. All of you please verify whether it's correct or not. Can we draw something like this? This will be the load at the extreme end and one more load at this end. Can I say this together will be just having similar condition like this? Can we represent it like this? And of course, some gap, you can say that D. Check it out. Can we represent it like this? Can we represent the bending stress or bending moment something like this, axial loading condition wise? Why no? Why no? See, this and this will together create the bending moment like this only, right? Then what's the difficulty? Then what is the difficulty? Same thing only, right? Both are having same meaning. I mentioned already, both are having same meaning. Check it out, right? Yeah, I just want to say that that's why we are saying axial stress to be normal stress and bending stress is also normal stress. It's not something else. Normal stress as well as bending stress, both are same thing. Bending stress also, in bending load also, both are acting perpendicular to the cross section. But the difference is that it is not creating any movement. And once you apply the load something like this, that is also normal to the cross section. And that is going to be creating the movement like this about the centroidal axis, That's a difference. No, that's a different you will be getting. Now, what I'm going to do, I'm going to zoom it. I'm going to take the cross section, cut it, and I will draw this one. P will be acting like this. What will be the reaction forces? You know that whenever the load will be applied, whenever they will try to deform that body, resistance force will be developed like this. And for this one, like this. Yes or no, guys? Check it out. In fact, it will be acting throughout the cross section. In fact, it will be acting throughout the cross section. Check it out. Please check it out. Please check it out. Yes. But what you are observing, guys, you are observing one thing. Sir, what we are understanding, sir, magnitude, like if the load is applied exactly at the centroidal axis like this, then if I cut this section, all the having similar magnitude, what we have seen, the reaction forces will be there, is totally acting uniformly in the cross section when I apply the axial loading. But sir, when I apply the bending loads, the stress distribution is not uniform. It's a non-uniform distribution is there. Something like this, sir, I'm getting like this. Can anybody tell me why is it so happening? It is decreasing. Again, it is increasing in the opposite direction. Sometime we used to show like this. Sometime we used to show like this. Some textbook they represent like this. Some textbook they represent like this. Why is it so happening? Why it is not uniform? Something like this. Why it is just decreasing and zero at one location, and again at the maximum at the what? Again it is maximum at the extreme fiber. Each layer is called as fiber, remember. Each layer is called as extreme fiber or intermediate fibers. Each layer, we assume that the beam is made up of so many layers. Each layer is called as fibers. Why is it so, my dear friend? That is what my question mark. Why it is so? Why the non-uniform distribution is there? Tell me guys, try to participate. At least just see from the perspective of centroidal axis here, something like that, right? Try to see and visualize and just tell me the answer. Tension compression. Yeah, tension compression, that is fine. See, yeah, top and bottom is there, but I can draw like this also, right? Sir, it is like this. It's a tension. Sir, after this, it will compression. Why this I have not drawn? This is incorrect. Why? Here also tension compression is there, but why it is just it is just decreasing and again it is increasing like this. Remember, it is a bending stress distribution. Remember, it is a not bending moment distribution. It is a bending stress distribution. Understanding my point or not? And this one is what? Axial stress distribution. All of you are able to follow me or not? Tell me, guys. All of you are able to follow me? Perfect. Now, the reason behind that is sorry. The very much reason is hidden behind that distribution is that it is varying linearly, my dear friend, right? First thing is that it is varying linearly with respect to the distribution that has been happening with respect to the distance from the fiber, each fiber. That variation is linear. How? That is going to be proved. Do not worry. That we are going to see in the bending stress equation. That we are going to see in the what? Bernoulli equations. Not fluid mechanics Bernoulli. I'm talking about this particular bending, bending stress distribution. Whatever the bending equation we have, that we are going to see. Through that, you will understand why it is varying linearly, my dear friend. That is also numerical wise, formula wise, but practical wise, try to follow me. Try to follow me. This particular load was applied exactly at the midpoint, right? Exactly at the midpoint. So all the materials are facing the pain. Whatever the pain is happening because of this loading condition, because of the axial deformation, all are suffering with the same amount. All are going to follow the same kind of nature. But here what is happening? Here what is happening? Top fiber we are applying the load. Top fiber we are applying the load something like this, and bottom fiber we are applying the load something like this. There is some conflicts is there, some kind of difference is there between the nature of the load. One is trying to pulling this particular, upper fiber, and other one is what? Trying to push this particular lower fiber. Because of that, the nature of the stress in each material will be what? In each layer of the material will be different. And because of that, at some moment, there is a tension and there is a compression. While changing the magnitude from the, basically, while changing the direction from the tension to compression, at one location it will be there where it will not feel that any bending stress will be there. What layer we call that one? Neutral layer. The neutral layer is nothing but the layer where there is a no tension or compression. That means they will not be pulling and pushing of this particular layer, my dear friend. Understanding or not? Otherwise, upper fiber will be just stretched out. And the lower fiber will be what? Getting compressed. Understanding or not? That we will understand through the, again, one more diagram I will draw. Through that, it will be clear. Right? So please note down whatever the things are there in the slides. So now once it is done, then please let me know. Note on the bending equation. Bending equation. M by I, that is going to be equal to sigma by Y. And that is going to be equal to what? E by R. Very, very important, guys. Most important equation in theories of simple bending, which gives the relationship between various characteristics of the beam. M is what? Bending moment. I is what? I is what? Moment of area. Moment of inertia, right? What about sigma? Sigma B. Here you can just note down M is nothing but bending moment. I is what? Moment of inertia. Sigma is what? Sigma B, bending stress. Y is nothing but the distance from what? Tell me, guys. Very important. Y is nothing but what? Distance from the what? Distance from neutral axis. Perfect. When we cover this particular bending equation derivation in the GATE course, then it might be clear. But as of now, for the HL examination, we don't require any derivation, guys. Again, that will be time wastage only. Directly remember this bending equation, believe me, right? And in that derivation, you will understand. Suppose this is the this is what we have the cross-sectional area. Suppose cross-sectional area we are taking. This is what the one neutral axis where the bending stress is what? 0, my dear friend. Like this distribution will be there. Where the bending stress is 0, here it is maximum. Here it is maximum. Suppose it is symmetric one. So at this location, the bending stress is 0. And from that location, we are going to take the distance. In the derivation, it will be clear. But here, just note down for your basically, understanding the distance from the neutral axis, right? E is what? Young's modulus. R is nothing but radius of curvature. What do you mean by the radius of curvature? Anybody? It's not the radius of the shaft. It's a radius of the curvature. What do you understand by the radius of curvature? Any one of you? See, when you take the beam and when you apply this particular bending moment like this, then this particular beam will bend like this. This particular beam will bend like this and it will make a curvature which is having a radius R. Which is having a radius R, my dear friend, right? Please note down, very important. Very, very important. When we are going to apply the bending moment, it is going to be something like this, my dear friend. Now you can follow the lower fiber. The lower fiber will be what? Under compression or tension? The lower fiber will be under compression or tension? Lower fiber will be under compression or tension? Compression, right? And the upper fiber will be what? Under tension. Under tension. It is trying to stretching out the upper fiber and compressing the particular what? Lower fiber. For this beam, for which condition? Hogging condition. For hogging bending moment, the upper fiber will be subjected to tension and the lower fiber will be subjected to compression. That means this fiber will be subjected to tension and this one is going to be subjected to what? Compression. The third assumption is saying that whatever the E value is there, E value is same for tension as well as compression. Suppose you want to calculate the maximum bending stress in tension, then what will follow? Sir, you will follow this equation My by I, and we also write M by I by Y. I by Y we call moment of inertia by distance, we call section modulus M by Z. So in that calculation, my dear friend, suppose you are calculating through this formula, there is no requirement of E. But suppose you are using this two formula, then you might be required the formula E into Y by R. Suppose you are calculating for tension, E value will be same. Suppose you are calculating for compression, again E value will be same. Understanding? Y tension, Y compression. Check it out. All of you understanding what I'm talking about? The assumption number 3. The value of E is same in tension and compression. Is it clear now? Perfect. So just note down. So yeah. So upper fiber will be what? For this hogging bending moment, the upper fiber will be subjected to tension and the lower fiber will be subjected to compression. But somewhere there's a no compression tension. Nothing is going to be happening. No compression, no tension. That layer we call neutral axis. That particular layer we call neutral layer, right? Note down. I think done, right? All of you. Is it done? Let me know. Please check it out. Perfect. Note down distribution of the bending stress across the section. Now there is a misconception in any, if you follow any textbook, in the cross section only they are showing that bending stress distribution like this. In the cross section itself they are showing. It's wrong. In the cross section we cannot show that. Bending stress can never be shown on the cross section, my dear friend, right? Let me show that. Let me prove it. Suppose you are going to apply the loading condition like this. I'm applying sagging bending moment and I'm going to follow the distribution will be suppose something like this. P and P amount of load I'm going to apply such that it is able to create the movement in this direction, which I have shown in the left hand side figure. Now, so here, my dear friend, what will happen if I just cut it? If I just cut it out on this cross section, because of this, to resist this one, I'm going to apply the load like this, and this magnitude will keep on decreasing, and it will become 0 at the neutral axis. And how to find the neutral axis? First of all, tell me, for any cross section, how to find the neutral axis, whether it is the center of gravity or not of that particular cross section. The neutral axis location will be center of gravity. That means centroid for that particular figure or not. Centroid of cross section or not? Tell me guys, whatever the neutral axis location is there, can we say centroid? Yes, perfect. So suppose for the midpoint, it is going to be acting like this. And now to resist this load, it is going to be acting like this. And the magnitude will keep on decreasing, and it will become zero at this neutral axis. Something like this, my diagram will look like. My diagram will look something like this. Some of the Indian author textbook, they used to represent it like this, or some of the authors, they used to represent it like this. Instead of drawing like this, they can directly take it out to this side and they draw like this. So where you are seeing the bending stress distribution, are you seeing in the plane of cross section or a perpendicular to the plane of the cross section? Tell me. Are you seeing in the plane of the cross section or in a perpendicular to the cross section? Yes, yes. Tell me guys, fast. Perpendicular to the, see, in the plane of cross section, we can never show that. See, this is the plane of the longitudinal axis. How the cross section will look? Cross section will be perpendicular like this. That is the cross section. Now, whether we are showing the any cross section means in that cross section bending distribution? No. So bending distribution can only be seen. No down, can only be seen in a plane perpendicular to the cross section of the beam. Lot of mistakes are there in many of the textbook. If you follow, they directly represent this distribution in the plane of the cross section only. That will be depend on what, which type of loading you are applied, whether bending load or twisting load. Twisting load can be seen in the plane of the cross section, right? That's a very, very important thing. Now, once it is done, then please let me know. Distribution is very important, highly important. The top fiber will be what? Under compression, and bottom fiber will be what? Under tension. There's no doubt. So now, so bending stress, if somebody will ask you, bending stress, if somebody will ask you how to calculate, simply calculate by this equation, my by I. That means m by I sigma b by y e by r. Either use this equation or this equation. It depends on the equation, what the data they have given, right? M by Z, where Z is nothing but section modulus. We will learn more about section modulus. Do not worry. M is nothing but bending moment. M is nothing but bending moment. Once we see any numerical, the things will become more clear how to calculate the bending stress actually. And Z is nothing but section modulus. Section modulus. Highly important, guys. Similar kind of thing we will be having the shear stress also. The shear stress. In that shear stress, whatever the next topic will be there in the same chapter, chapter 3 only. That distribution I will show in the plane of cross section, right? Now, once it is done, please let me know. Once it got done, please let me know. Perfect. Perfect. Note down section of strength of any section. how to calculate the strength, how much of strength, if any particular beam is there, how much amount of bending moment it can able to resist, and that is what we call strength of that particular section. Sometimes we call flexural strength of that section. How much of movement of resistance it has been offering, that will directly proportional to what? Suppose sigma is constant, so M will be directly proportional to Z, section modulus. The stronger the section modulus, the stronger will be the section modulus, the stronger will be what? The strength of that particular section. Now somebody will ask me, sir, how to calculate that section modulus? That is what very important, right? So remember my dear friend, I is calculated automatically by default about the neutral axis, not about bottom axis or top axis. It is top layer or bottom layer. It has been calculated with respect to neutral layer or neutral axis, right? Very important. So yeah, suppose sigma B maximum is less than sigma permissible. And what is the sigma B maximum? M by Z maximum. It must be less than sigma permissible. So what should be the value of moment of resistance? It must be Z neutral axis into sigma permissible. Note down, very important, where Z neutral axis will be I neutral axis divided by Y maximum. Y maximum. Maximum to maximum moment of resistance will be what? This much only. Not this one. Now tell me left hand side or right hand side, which is the moment of resistance? Now there is a logic. Which one will be the moment of resistance? Tell me, guys. This one or this one? If I'm saying that moment of resistance that has been offered by that body, so this one, this together we call moment of resistance. Whatever the external moment you are applying, that must be less than moment of resistance. Otherwise, your material will fail. Right? And what about Z maximum? It is different than Z. Z is simply I neutral axis about by Y. If I calculate Z neutral axis, then I neutral axis divided by Y maximum. Y maximum. Understanding or not? All of you are understanding? Tell me, guys. Sorry. All of you are understanding? Yes. Perfect. Now somebody might be thinking, sir, what is the Y maximum? See, suppose I'm taking a rectangular cross section which is having a width B and depth D. Where will be the centroid? The centroid will be here, d by 2 distance, d by 2 distance. Automatically, what will be the Y maximum? D by 2 only, right? Y minimum will be 0. Now for calculation of the Z neutral axis, suppose that if I'm calculating for this rectangular one, you know that the moment of inertia about the neutral axis, BDQ by 12 by D by 2. So what will be the answer? BD square by 6. Understanding? This will be your neutral axis. All of you are understanding or not? Why distance we are taking from the neutral axis? Maximum will be the distance from the top to the neutral axis or bottom to the neutral axis. Sometimes the distance will be different. Suppose we are calculating for T section. Suppose T section will be given to you. So centroid will be somewhere here. This will be my neutral axis. Now this will be suppose that Y1 and this will be suppose that Y2. Now if I'll ask you Y maximum, what you will put? The larger of Y1 and Y2. Understanding or not? All of you are understanding what I'm talking about? Yes or no? Perfect. So put a note and note down. Put a note and note down. Now, once it is done, then we can have only one discussion on one problem. Then we wrap up today's session. Tomorrow also we have the class. There is a, schedule changes will be there. Whatever the 9th March class will be there, that has been preponed to 8th March. So tomorrow also 6 p.m. to 8 p.m. we have the strength of material class. That will be my 5th class, and that is I'm going to cover shear stress and its distribution, and I will try to cover it all along with this numerical of the bending stress and distribution. Apart from it, the shear stress, we are going to cover, deflection also. We will start 1 or 2 numerical on deflection, right? Understanding or not? So more and more amount of M will be keep on increasing. Sigma will also keep on increasing. Sigma B will keep on increasing. At some point of time, sigma B will be more than sigma permissible. At that point, material will fail. Yes or no? That is what the meaning of this statement, right? Correct. So what we can do, we can have the very small numerical we can have, right? Yeah, we will try to solve this question. We can take small one. Moment carrying capacity means moment resistance, simply MR. And MR, you know, that directly proportional to Z about neutral axis. Maximum moment of resistance offered by the body will be what? Z about the neutral axis. And you have the two cross section. One is exactly the square, and one is what? Circular cross section. Now you need to calculate which one will be able to carry more amount of bending load. Suppose you are making your house beam is made up of square cross section or circular. That is what you need to decide, right? So ratio of the moments for moment of resistance for square to the moment of resistance for, circular cross section, they are asking. That will be what? Z of square cross section about the neutral axis to the Z of circular cross section about the neutral axis. So what about the Z? Iy by y. For the square one, I'm just representing like this. I by y maximum for circular cross section. So what will be the answer? D to the power 4 by 12. D to the power 4 by 12 divided by y maximum. What is the y maximum we have? D by 2. So 6 dq by 6 dq will be the, sorry, dq by 6, that will be the answer for this one. And what will be the answer for this one? I for circular cross section, pi d power 4 by 64. And y maximum is what? Y maximum is what? D by 2. So now if you just take the ratio, dq by 6, pi d power 4 by 64, into d by 2. So yeah, so this will cancel out. 16 divided by what? 3 pi. Are you getting same answer? All of you, please verify it. Perfect. So which one is able to resist more bending moment? The square cross section will able to handle more bending moment, more bending load, simply. More bending load, simply. That will be the answer. So your beam should be made up of square cross section rather than, circular cross section. So that is the correct formula wise. But can you please explain physically? I'm not getting the feel actually, sir. Some of you might be thinking, sir, I'm not getting feel. Can you please elaborate with conceptual clarity? Yeah. So I will take hardly 2 minutes of time. Let me just give my point about that, and then we close the session. Now, you know that the bending stress is what? My by I. M by I is constant. So sigma V is directly proportional to Y. That's the reason it is varying linearly, right? Yes or no, guys? Check it out. Sorry. Perfect, perfect. Focus, focus. Upper fiber, maximum bending stress is there. Lower fiber, suppose maximum is there. And it is keep on decreasing layer wise. Your square cross section is saying that I have provided enough material on the top so that it will able to resist. In fact, not on the top, at the middle also. In fact, middle one, there is no use if there is no material also, because hardly we have any bending stress. Zero stress is there. But what the circular cross section is saying, on the top, I have provided very less material. And at the middle, I have just more than sufficient enough to resist the bending load. Now, the scientists will come, those who are judging this context of, who will be able to resist more bending moment, and he will say, why you are making fool? At the top, you are placing very less material. At the bottom, you are placing very less material. And you know that the bending stress is maximum at that point. Keep more material. Keep more material. Understanding or not? Why it will able to handle more bending load than this particular, circular cross section? So in two ways, I explain you by the moment of resistance and by these particular concept, which I explain you now. At the top, at the bottom, material should be more so that they can able to resist more bending load. See, who will resist? Not particular any, you can say that some genius person or maybe some imaginary person will resist, right? There has to be some material to resist this particular load. If we are applying any load, there has to be material. There has to be material. Some material, some person should be there to resist that one. Right or no? Tell me, guys. Now it's clear why it will able to handle more amount of bending load. Means square cross section is better than this circular cross section. In fact, I section is best among all. See, I section. He said that full-fledged I have provided the top material and bottom material, and at the middle and somewhat middle section I have kept very less material. So that's the reason. If you just see the cross section of the railway track, they are made up of I cross section. Beams, if you just follow the beams of your house, look at very carefully, they are I sections, so that they can able to resist more bending loads. Right or no? Yes or no? Tell me, guys. So in that sequence, put a note and note down. Z of I section is more than Z of rectangular section, is more than circular section, sorry, square section. Then this particular circular will come, then square diagonal will come. Square diagonal will come. This is what the sequence of the, for the given area I'm saying. For a given area must be constant. Otherwise, the things will be complicated, right? Moment of inertia might be changes accordingly. So section modulus will be highest for I section, and in this direction, bending load carrying capacity will be increases. Bending load carrying capacity increases in this directions. When we move from like this to like this, it will keep on increase because Z will keep on increase, right? Done. All of you have noted down? All of you have noted down? Okay, so thank you all. Right. Yeah, we'll see tomorrow's about the remaining sections? Yeah, thank you all.